Hi everyone, today I'm gonna talk about diffusion analysis on aldo reaction related molecules by effective fragment potential molecular dynamics simulation. So for the background, what is molecular dynamics? So it shows the classical particles and which is simulated by solving Newton's second equation. So which is like this equation, the first equals the ma. And then the first is the derivative of potential energy, which is V in the equation at position R. R is a vector containing the coordinates of all particles in Cartesian coordinates. And this figure shows typical time scale, and then usually in MD simulation, the time step is 1 femtosecond. And because it is limited by the highest frequency vibration in the system, typically to 1 to 10th of the period of that vibration. And in this figure, the water dynamics, which is around the nanosecond, and then the simulation up to the 1 nanosecond required because it can show the work properties such as diffusion coefficient. And for AV initial molecular dynamics is based on the quantum Schrödinger equation, while its classical counterpart relies on the Newton's equation. So molecular dynamics relies on semi-empirical effective potentials, which approximate quantum effects, while AV initial MD is based on the real physical potential. So this is comparison of between two different molecular dynamics. So for the classical molecular dynamics, it performed on the basis of empirical force fields, which were parameterized using both AB initio and high-quality experimental data. Molecular mechanical force fields purely based on AB initial calculations usually do not have a satisfactory performance in predicting the molecular properties of liquid or solid phases. And it works well for simple particles such as noble gases, but it usually performed poor for covalent atoms and metals. But it is very fast and it is available to perform MD simulation for large systems. And then for AV initial molecular dynamics, it performs a full quantum calculations of electronic structure at every time step for every configuration of an atomic nuclei. But it requires really high computational costs because of like higher numerical effort. So what is the effective fragment potential method? So EFP is a model potential derived from first principles. So there is no empirical parameters in EFP. So this computational method is developed to describe intermolecular interactions, and it is using the rigid internal geometry of molecules. And to use EFP, the make EFP required, and which is using Hartree-Fock equation. So in the EFP methods, there are 5 different molecular dynamics. And then the first one is Coulomb term, which means electrostatic interaction by using distributed multiple moments located at atom centers and bond midpoints. And second one is polarization term, which is computed by the localized molecular orbital dipole polarizability, and induced dipole is iterated to self-consistency, and this is the many-body polarization. And the third one is dispersion term, which is the interaction between induced multiple and induced multiple. And then the exchange repulsion term, which is calculated by an expansion from intermolecular overlap. And the last one is charge transfer term, which is the interaction between the occupied orbital from one fragment and the virtual orbital from another fragment. And this is for the experimental background, and the aldo reaction between the paranitrobenzyl aldehyde and acetone is occurred with the heterogeneous catalyst, which is the major silicon nanoparticles with the hexane solvent. And for MSN, the Dr. Igor Soloin group in Iowa State University, they compared two different sizes of MSN. One MSN is 3.6 nanometer white pore, and the other one is 2.8 nanometer white pore. And when they used which means larger pore size of MSN, the reaction rate increased by the 20 times. And so this experimental data shows the rate of the reaction was limited by the molecular diffusion within the narrow pores, because if the pore size is getting bigger, and it is more easier for the reactant to get inside to the MSN, and then the reaction can be initiated with the active site with reactants. So in this reaction, diffusion is the key for initiating the reaction. And the diffusion depends on the intermolecular forces. So to calculate diffusion coefficient, I used Acetone relation, and which is using the mean square displacement and divided by the 6 and the number of molecules. For computational method, I use the standard basis set, which is the triple zeta for make EFP. And all the MD simulations were performed by MVT ensembles, and then the temperature at 300 K, and then the periodic boundary condition is applied, and the time step was 1 femtosecond. So there are 4 different kinds of system, which is pure acetone and pure hexane, and the mixture of acetone and hexane. And then I added 1 paranitrobenzyl aldehyde, which is the main reactant in the aldo reaction, to the mixed solvent. So this is the pure acetone MD simulation, and then the graph is the time versus the mean square displacement. And then the self-diffusion coefficient based on this graph was 3.5, 10 to minus 9, and the experimental data was 4.77. So which is very close to the experimental data. However, the whole MD simulation, it is up to about the 12 picosecond. So it needs longer simulation. And this is the pure Hexane MD simulation by EFP method, and the mean square displacement shows a little bit curve, which is not very straight. So the first part will be the ballistic motion between molecules. So definitely it needs longer simulation to get a straight line for the MSD, but until now, based on this result, the self-diffusion coefficient is 4.46, and experimental diffusion coefficient is 4.21. And this one is the mixture of acetone and hexane, and it is based on 1-to-1 volume ratio. And this one is the radial distribution function for the between the oxygen atom from acetone. So red line is from the pure acetone, which I already mentioned before. And then the blue line is the line for this acetone hexane mixture. So it is very obvious that the distance between oxygen of acetones, it is more closer compared to the pure acetone. And this one is for the equation for the mean square displacement for hexane and hexane and acetone in the mixtured solvent. And also both lines are not very straight enough because the first part it shows a little bit of ballistic motions. But based on this MSD line, the self-diffusion coefficient for the acetone is bigger than the pure acetone, and also which is same for the hexane, the diffusion coefficient is get larger than the pure hexane. This is my last system, which is I added 1-nitrobenzyl which is the main reactant in aldo reaction, and I placed it at the center of the simulation box, and then the solvent is the 1-to-1 volume ratio mixture of acetone and hexane. And these two are the mean square displacement curve for each acetone and hexane. And then again, the self-diffusion coefficient of acetone is got larger than the previous one. I mean, the larger than the pure acetone and larger than the acetone and hexane mixture, and which is the same for hexane too. So which means in this system, the acetone and hexane moves more actively compared to the previous system. And this one is the mean square displacement for nitrobenzyl in the system. And then it is not very quite straight enough. And this is my challenge to get the diffusion coefficient of nitrobenzyl. So maybe this means I need more simulation time to get the more reasonable the mean square displacement. Like, as for the future plane, I need to investigate the radial distribution from MD result, and then definitely longer MD simulations are needed. And in the future, analyze the MD simulations results for translational and rotational diffusion tensor. I want to thank to my advisor Mark Gordon, and then this one is a collaboration with um, Jim Evans in Iowa State University, and then also I want to thank to the Dr. Young Han and and for EFP advice from Dr. Peng Su and Dr. Torsapun. And then thank you to Gordon Group. Thank you for listening.